bit later. Yeah. Sorry, let me just make sure. So yeah, I mean, we'll pick up from where we left last time. So last time we stopped at trying to understand how we perform projection. So if we have, sorry, let me just get the pen. So if we have a certain like 3D world, 3D point, how can we project it to a 2D point in image coordinates? And we discussed how, like we discussed two things first, like we discussed how to use the focal length. So if you remember even from last slide, at the end, we know that the projected 2dy is just the focal length multiplied by the 3D coordinate, coordinate y component over the z component, which we call the depth. And then we talked about how we also use add the principal, so this is the y component of the principal point. So we talked about the principal point as another part of the projection matrix. So this was what we ended up, and we separated this 3x4 matrix into this small 3x3 matrix, which we called camera intrinsics, which has so far the focal length and the principal point as the parameters, and multiplied by just simply identity. So this formation is just like the identity followed by the like on all zeros column. So that's what we talked about, and multiplied by the, so x bold is the 3D point in world coordinate. Now, we didn't talk about how to continue from like beyond the camera intrinsics. There is something called camera extrinsics, which we will discuss now. So I'm always assuming that I'm already in camera coordinates. So remember, let me go a couple of the slides back just to refresh. So if you remember this, if you remember this slide, we always had everything with respect to the camera center, and like with respect to like the camera coordinate system. And we defined like the focal length, the depth, and so on. So this 3D world point was with respect to the camera, like some camera coordinate system centered at the camera, where the origin is the camera center. But that's not necessarily the case. So you might end up having, so this is here the camera, and then I have some global, other global coordinates, like let's assume it's the world coordinates. Or it could be any other coordinate system, and your 3D world point is with respect to this coordinate system. So let's call it the world coordinate system. Now you need to make sure that you transform from one coordinate system, from the world, to the camera, so that this point here is actually with respect to the camera coordinate system. So this is what the step that we stop at, and this is what we will be looking at now. So here, what we're looking for, if like how to go from world coordinate, I just prefer to make everything with respect to this, like having some world coordinate frame, and then transforming it to the camera coordinates. So in this case, so yeah, here, this assumed the camera center is the origin, and we assume that the principal axe, so if you remember the principal axe that goes out of the camera center perpendicular on the image plane, if you remember, so this principal axe looks down the z-axe. So the depth is estimated there. So now we're going to make sure that we go from here to here, from the world coordinate to the camera coordinates. But before doing that, we need to understand that there is a difference between when you're doing a transformation on an object versus transforming your coordinate system itself. So if I'm trying to, like you can call the basis of your coordinate system like the IJK. Like we're gonna apply some transformation on the coordinate system itself instead of applying it directly on the object. Let's see first if I have a point here. So this point P1, 2, and 4, So if I apply, and this is, again, this is part of transforming objects normally. So if you're transforming objects normally, I want to construct my matrix that will do a translation tx ty equal with 1, 1 and 1. What do you think would be the transformation matrix in this case? So I'm working 2D now, not 3D, and I want this 0.24 to be transformed. So I have here 2, 4, and 1, because we always work in the homogeneous coordinate system. What would be the transformation matrix that I will apply that will do this translation? What do you think? Just as a refresher, I know it might be a simple question, but as a refresher, anyone remembers?
I think it will be 10 tx.
Exactly. So tx, which is 1 at this case, yeah.
Oh yeah. Then it's 0, 1 ty and 0, 0, 1.
Exactly. Thank you. So this will be, thank you. So this is the normal, like how you would normally transform an object, where the object is constructed at least of different points. So this is a point on an object. Okay. So this will be just, this will be just taking 2, 4, 2, 3, 5. And this will be like what you said, will be the transformation matrix. Now, if I want to translate the coordinate system itself, that's different. So let's say I have here this red coordinate system. So this is my x and y. And I have here point P1 and point P2 with respect to this coordinate system. So P1 is at 2, 4, P2 is at 3, 5. Now I want to translate the coordinates tx equal 2 and ty equal 4. So normally the transformation matrix, if we're trying to do a translation, we'll just make 1, 0 tx as we agreed. So like 1, 0, 2, 0, 1 ty, which is 4, 0, 0, 1. But that's if I'm trying to transform the object itself. The coordinate system is fixed. We're not changing the coordinate system. Now I'm trying to change the coordinate. So if you're trying to change the coordinate, it's actually going to do like all the objects will get transformed with the inverse of the operation that you're, the inverse of the transformation that you're applying to your coordinate system. So let's say here, you see, I transformed it with 2 and 4. So originally, it was the origin was at here, at this point, and I wanted to translate it so that it goes to 0.24. So now the new coordinate system should start at 2, 4. So in this case, what will happen to this point and this point? Because we're transforming the coordinate system itself, not the points, everything will get translated the inverse. So this will become 0, 0, right? Because so we'll have here -2 and -4. And this one becomes 1, 1, right? So, and this is, now this is like all the points, like all the objects and the points on the objects are going to be transformed with the inverse of the operation that you applied on your coordinate system. So anyone has any issue with this concept? So far, we have seen it in a translation. So we have gone from the original coordinate system, translating it with 2, 4, and we see that the output becomes, now this is the new like the new points after transforming the coordinate system. And we see here that we're using the inverse. It's exactly the same in the rotation. Let me just make sure anyone, okay, no questions. So it's exactly the same in the rotation as well. So if I'm trying here, so you see here this, I have this cuboid. I have this point here at 1, 2, 2. And this is just my, my coordinate system that I've picked. And I'm trying to rotate with -90 around the y-axis. Okay, so this is the y-axis. And -90 means that you're moving clockwise. So I'm moving like that, clockwise. Okay, so if I'm moving like that, this is what I'm trying to rotate. So, and with 90 degree, so the z-axis gets rotated, so it gets rotated here. And the x-axis gets rotated in place of the z. So you will see that the x became in the place of the old z. and the Z got rotated with this negative 90. Now, what will happen to this point? Remember, originally it was at 1, 2, 2. So we had this is length 2, and this is length 2, and this is length 1. Okay, so if you look into the updated point, you will find this is the positive of the Z, and I know that this is length 1, but it's in the negative direction, so the Z now became negative 1, and this point here, this part we know is length is 2, which is the Y, and I know already that this part, which is now the new X, because after the transformation of the coordinates, is its length is 2. So the point that was 1, 2, 2 got transformed into 2, 2, negative 1. So you see, this is another example of doing a transformation on the coordinate system. And we are seeing, so when we transform the coordinate system, at the end, the transformation happens on the objects, but it happens with the inverse of what we did on the coordinate system. So if we're doing here some rotation, and I'm trying to do negative 90, you will see that the final actually transformation that I'm going to apply is doing a rotation with 90. So the inverse, of rotating with negative 90 is rotating with 90 degree around the y-axis. So if you remember here, like this will be cosine 90 sine 90, negative sine 90 cosine 90. So this is rotating around the y-axis with 90 degree. And this is the final one. So if you take this one and multiply with your original point 1, 2, 2, and we still have the homogeneous coordinate. We're in a homogeneous coordinate system. We have the homogeneous coordinates. Sorry, we can multiply it by our 3D rotation around the y-axis with 90 degree, and end up having the final point, which will be 2, 2, and negative 1. So if you do this operation, you will find that it does map. If you do this multiplication, it does map to this new point. So we all agree now that when we started with the translation, if we translate like the coordinate system, all the objects get translated with the inverse, which is like the negative of the translation. Similarly, if we do a rotation, all the objects, if we rotate the coordinate system, all the objects get transformed with negative the rotation. So instead of negative 90, we go for 90. And that's the one that gets applied on the objects. So now you understand what's the difference between doing a transformation on the objects directly versus doing it on the coordinate system. Does it make sense? Or anyone has any questions? Do you have concerns? Like, do you feel like it's too, it's easy, or do you feel like it's hard to grasp? I mean, we can do a bit more exercises here if you feel it's hard, but if things are okay, like no one is commenting. So I'm assuming things are good.
Sorry, can we do some more examples? I don't think I really get it.
Oh, okay, sure. So you know what? Let's let me confirm. Is it the rotation that confuses you or the translation?
So the rotation, especially where you're saying that doing it on the coordinate system instead of the object itself.
Gets confusing. Okay, I get what you mean. Sure. I mean, we can do another thing. We can so let me, I think sorry, I forgot to open the video. My mistake. Anyway, let's try another one. Let's try to look into the same rotation, like we're trying to rotate with negative 90 around the y-axis, but we're gonna apply it on another point. So let's go for this point here, okay? So this point here, First, what do you tell me? Like in the original coordinate system. So I have here, this is X, this is Y, this is Z, and I give you the length. So this cuboid, it's 2 here. This part is 1, and this part is 2. So what do you think would be the coordinate of this point? Let's start on the X. So its X component is what? You can type in the chat. So X component, so this point here lies on this plane, like this plane here, where the X is gonna be equal to, what do you think? So give me the components of the X, Y, and Z. Let me check if you typed it in the chat. Do you have a, I think you were, Daniel, you were the one asking, or who was asking, sorry?
Yes, it was me.
Yeah, so Daniel, can you help me? So if I'm trying to get this point here, in the original one. So this one, what was at 1, like X component is 1, and this is 2, 2. So the point in the back.
Okay, that'll be like the origin.
Exactly, it's at the origin, so it's 0. That's for the X. What about the Y and the Z?
So the Y, let me see.
So it's 0 and then?
So it's the Y, I think the Y is the same.
Exactly. And the Z?
The Z also seems to be the same. It's also on top of the keyboard, right?
Yeah, exactly. Yeah, so it will be 0, 2, 2. Okay. Now we rotated, thank you. Now we rotated the axes so that X is in the position of the Z, and the Z is now on the, like, think of it like it's lying now on the floor, but in the negative direction. Okay. So it's like, I don't know how to say it in English, but like it got rotated in the back. So now this is the new X and this is the new Z. Okay. So if you have this point, which was supposed to be 0, 2, 2, it has to be now updated based on this transformed coordinate. So even from the figure, let's not go through doing the matrix multiplication or anything. From the figure here, what do you think would be the updated point? So the 0, 2, 2 will become, this point here is what? So look to the fact that where? Yes. So I just want to give you here again, this is 1, this is 2, and this is 2. Okay. So for the X, what do you think would be the updated X?
Can I quickly ask a question? I hope I don't sound dumb.
No, it's okay. Don't worry.
Okay, so when you say we rotate it, right? Are we rotating the object, or we are rotating our own perspective of looking at the object?
You can think exactly the second one. So we are rotating our perspective. So think of the coordinate system. This is how you look at the object. The object hasn't changed.
Itself. All right.
But the object will change because our axes, like it appears to have changed because our axes themselves have
relative to the object.
So the perspective has changed. Yes.
So
now this point, you see this red lines are the new axes. So what do you think would be the X in this case? So this is the X here. So what do you think this point will be the updated X, the updated Y, and the updated Z? So the updated X, you see here, this part, this is 2, right? Do you agree? All, or do you have any issue with the fact that it was originally 0, but now it will get updated to become 2 because of the fact that we rotated our perspective of it? Or you're still confused about that part?
No. I think I'm getting it now. I think.
Oh, okay. And I see some people. Okay. Sorry, Grace. I just saw So you're saying 2, 2. So it's 2, 2. Yes. So here, X is 2, Y is still 2. Yeah. and the Z becomes 0 actually.
0.
Yes. I'm looking at the point in the back here. So the point in the back is exactly on the, you see here, it's with respect, this is the origin here. So this will be like this whole new, this all this rectangle is, will have a Z equals 0. So this is the point, okay? Now, in order to reflect this, like what we're trying to construct the transformation that will get us from 0 to 2 to 2 to 0, because of the fact that we rotated our perspective. And I like how you stated it, Daniel. We rotated our perspective of the points or the objects. So let's go through it. Let me just remove, sorry, because it's getting messy. Let's just discard and start again. So here, we're again going from this point, which is 0 to 0. So if we put here 0 to 1, and then we get the new point. Let's just do like, if we do the matrix multiplication, you will find that this is exactly what it's doing. So if you take this row multiplied by this vector, you'll end up having here 2. This row multiplied by this vector, you will end up having 2 again. And then this row multiplied by this vector will end up being 0, because you're already at 0, and then 1 for the homogeneous coordinate. So you see this, which is the rotation around the y-axis with 90, not negative 90, with 90 degrees. So we did the inverse of what we started with. So we started with transforming the coordinate system itself with negative 90, ended up applying a rotation of 90 on all the object points to get the correct transformed points, okay? So this is how transformation on objects differs from basis. We are always using the inverse when we're transforming the coordinate system itself. Anyone still has any confusion, or things are cleared up? Let me check if there is any issues in the chat. Yeah, I think I'm assuming these are, so no one has any issues, so I'll continue with this. So remember what we were trying to do? We wanted to go from world coordinates to camera coordinate. So if I have some point here with respect to some world coordinate that is defined in whatever the context that we're working with, I want this point here to be with respect to the camera coordinate system. So what we're going to do, we're going to do an inverse of the rotation. So this is a rotation matrix that will do the inverse. So it's a 3 by 3 matrix. And we're going to do the inverse of the translation. So we have here negative C. So at the end, regardless of how you formulate it, but we do understand that we're going to use the inverse of the rotation and the inverse of the translation to go from world to camera coordinate frame. So negative C here is whatever this point is defined. And this is the original 3 by 3 intrinsics matrix that had the focal length and the principal point. So this part, which is at the end will be a 3 by 4 matrix if multiplied together, but you can think of the rotation and the translation that is corresponding to the camera coordinate system itself as the extrinsics of the camera. And extrinsics because it's external properties for the camera. So where the camera is located, it's an external property of the camera with respect to some world coordinate. While the intrinsics, sorry, like the K matrix that had, if you remember, had the focal length, the px, the py, it's internal parameters, meaning that, yeah, I mean, it is literally some property in the camera internally. It's regardless of how its location externally with respect to the world frame. So this is the final projection matrix. It's only remaining one last part. Yeah, so yeah, nothing here. Yeah, here. So the last remaining part for our projection is taken into account the fact that in CCD sensors, you might end up with non-square pixels. So this is not sufficient because this focal length is actually measured in millimeter. And then we're trying to project, remember here, this projection is going for pixels. So this is the X, the Y, and 1, homogeneous coordinates, but the X and Y in pixels. We're not talking about millimeter. Same for the principal points, which is defined in millimeter. So what we need is to add something called this MX and MY. So these are telling you the number of pixels per millimeter. And that is an internal parameter in the camera. So if you take this, it becomes, if you take this MX and multiply it by the focal length, it will give you the focal length in pixels. So remember, this is in millimeter, and this is giving you how many pixels in 1 millimeter. So multiplying, you will get the focal length in pixels. And this is also transforming our principal point. So everything lies in pixel coordinates. So we're now going to pixel coordinates. Same here. We're just going to use so MX and MY do not have to be similar. So it doesn't have to be square. So I can have, let's say, 2 pixels per millimeter horizontally, but then vertically, I have 1 pixel per millimeter. So whatever MX and MY do not have to be the same. And this is the final, like these are now considering all the, like the final projection from 3D world point to a 2D point. To just summarize, to make things, I hope with this summary, things will get clear. But we mainly go from world to camera coordinates, and we always use the inverse of the transformation. Remember, I'm transforming the coordinate system, so I'm doing the inverse with respect to like a inverse of the translation and the inverse of the rotation in order to have all the points here with respect to the new coordinate system. So now this is going to camera coordinates. The second thing is I need to project from 3D to 2D. So this includes this focal multiplying by the, including the focal length and the principal point. So this here, where we take the K multiplied by the X cam, like after the transforming it with the extrinsics. And then the final step is transforming to pixel coordinates, where we simply multiply by MX and MY. So the final K here includes going directly to pixel coordinates instead of like relying on this focal length in millimeter and principal point as well. So this in total, going from world to camera to pixel coordinates, this is the full pipeline. And at the end, what you end up, so you start from a 3D point, X, Y, Z, and 1. And you end up with, here, X, Y, Z, and 1. And you end up, after multiplying here by the K, you end up with X, Y, 1 in pixels. So going from 3D to 2D in pixel coordinates. So yeah, let me know. Anyone has any issue with the pipeline itself, like how we went from this to this, and from this to this as well? Okay, let me ask you as a refresher. So going from world coordinates to camera coordinates, do I use the extrinsics or the intrinsics of the camera? What do you think? So if I have here, just a reminder, actually, it's plotted here. If I have the camera coordinate system, and I have some world frame, and I have some point here defined with respect to the world frame, but then I want this point to be defined with respect to the new camera coordinate system. I'm using the extrinsics or the intrinsics of the camera in this case. What do you think? I'm using external parameters, like a rotation or translation of the camera, or am I using internal parameters like the focal length or principal point, things that are internal properties of the camera? You can guess extrinsics or intrinsics going from world to camera. External, thank you, Loyan, exactly. External, yes, yeah, extrinsics, and thank you, Daniel, as well. So we're using extrinsics because in this point C, we used here the inverse of the translation and the rotation. So this is to go for the camera coordinates system. And these are external properties. These are dependent on the location and the rotation of the camera. Now, when I go from here, the camera coordinates to the pixel coordinates, where I'm using this full 3x3 matrix, including the focal length, principal point, and the number of pixels per millimeter, that's like tied to the CCD sensor itself as a property. These are intrinsics. So here it is extrinsics that are being used, camera extrinsics, and here camera intrinsics are being used. Okay, so if this is good, what I'm going to go through now is understanding. So for the final projection matrix, this is the final projection matrix. Okay, this is the full thing. This full thing is divided into first a smaller part, the K. This is a 3x3 matrix. This 3x3 matrix is the we agreed it is the intrinsics. So it's the internal properties. How many degrees of freedom you think we have? So these are 5 degrees of freedom. So we only need 5 degrees of freedom to define, like we have 5 degrees of freedom that can control our camera intrinsics matrix. What do you think about the, so here, first, what is the shape of this R matrix and this full matrix here? What do you think would be the shapes of these matrices? So R, this is a rotation matrix. What do you think would be the shape of the rotation matrix, of this rotation matrix? Note that I have this like if you remember, we kind of separated. So we had this definition where we separated the identity and this augmented column. So what do you think? Anyone knows? Okay, I can ask another simpler question. So if I have originally, like, what do you expect would be the final shape of the projection, any projection matrix that goes from 3D to 2D? What do you expect would be the shape of this matrix, the size? So it's M by N. What is M? What is N? What do you think? It's a simple question. So yeah. I see. Yes, Grace. So what is M in this case? So M here. Yeah, I know. So what do you think would be the number I mean? So I'm going from 3D to 2D. So what do you think would be the shape of this, of the projection matrix that is taking me from 3D to 2D? Remember, I'm always working with homogeneous coordinates.
Will it be 3x3?
Okay, 3x3. This neglects the fact, so I have X, Y, and Z, but I also have 1. I always have the homogeneous coordinates.
So I'm talking about what would be the final thing.
You're talking, sorry, on what?
I'm saying that will the final output, right, will it be 3x3?
So
will it also include the homogeneous coordinate?
It will include, okay, so if it includes the homogeneous coordinates, we have input 4x1 and output 3x1.
Oh, yeah.
So we need a matrix that is 3x4.
Okay.
But so because you see here, so I agree with you, the intrinsics and the rotation matrices, all of these are going to be some 3x3 matrix here. But then we have the translation part. It is separated, but it is included. So we have this negative CX, negative CY, 0 and 1. This makes the full projection matrix 3x4. Okay. I hope this makes it clear. Thank you. Thanks, and thanks, Grace, as well. So we have the full projection matrix is a 3x4 matrix. And we talked about the camera intrinsics being 5 degrees of freedom. Now the extrinsics, remember we talked that the extrinsics, and these are terms that it's good for you to know. So anyone doing camera calibration, anyone trying to like work in robotics where you're trying to relate from the robot frame to a camera frame, all of these, you need to understand these concepts. So extrinsics, it is related to the external parameters of the camera. So external parameters of the camera, how many degrees of freedom? So external parameters, we talked that we have the rotation and we have the translation, and we're doing the inverse of them. So how many degrees of freedom for the rotation? How many degrees of freedom for the translation? And we're doing it in 3D. Everything is in 3D because we're still working on the 3D space before this part. So how many degrees of freedom for the rotation? How many things are changing? And the degrees of freedom are the parameters, the number of parameters that are changing. So if we go for trying to rotate, we can rotate how many degrees of freedom we need. Any suggestions? So we have pitch. Remember we had pitch, roll, yaw. That's what we called. Or the rotation around the x-axis, rotation around the y-axis, rotation around the z-axis. Remember that? So these are 3 angles. So we have here 3, plus we have the translation in the x, translation in the y, translation in the z. Oh yeah, sorry, this is CZ, of course. It depends also, like it's not necessarily 0. I think I forgot to add that part. But anyway, we have 3 degrees of freedom for the translation as well. So in total, we end up having here 6 degrees of freedom. So camera extrinsics is 6 plus the 5 degrees of freedom from the intrinsics. So if we're trying to do projection, the final projection, all of this is a 3x4 matrix, and the number of degrees of freedom is the 6 plus 5, so it's 11 degrees of freedom. Yeah, so it's called like this projective camera matrix, which is like responsible for doing the projection from 3D world, from a 3D world point to a 2D pixel coordinate. This one has 11 degrees of freedom. So anyone has a problem with understanding how we got this this number of degrees of freedom and how we did the projection finally? Is it clear or confusing? I know, so this is the part that it gets hard. I know when you start going to 3D, things get hard. But I'm hoping that through this session, if you have any questions, or yeah, if you have questions for the next time as well, like you can go through it, take your time on it, and if you still have questions, we can discuss it next time. But yeah, assuming no questions, I'll just continue. So the last part, so this already finishes the camera models. So you're now able to, you do know how to do 2D transformations, 3D transformations. So I know we're always we talked about like the translation, Euclidean, similarity, affine, homography, or like the, so we talked about all the transformations in 2D and 3D, and we talked about how to like go through the full pipeline of projecting from a 3D world point to a 2D pixel coordinate and how it actually happens in a camera in more details. I'll just show you some of the things that are in deep learning that needs this type of understanding of geometry in computer vision. So I'll give you here 2 papers, and then we can actually go through the like the next tutorial. So these 2 papers, I'm not sure if you so you're aware of the Oxford lab, the VGG lab. So I think it was from them, if I remember. Zisserman was the like the PI on the work, and so Andrew Zisserman is a very famous. I'm not sure. Have you heard about Andrew Zisserman? So this is one of the pioneers of geometry in computer vision. Like he has this book, Multi-View Geometry, which I really recommend as well. Actually, a couple of things in the slides here are from that book anyway. It's this book plus Richard Zaleski book. So these two books are really good for people who wanna go deep in computer vision. I would really recommend to go through them, especially if you're like continuing for PhD. So this guy, they designed this spatial transformers network, which is, remember when we discussed how we can take a transformation, which is like an affine, for example, and then apply it on a full image. So this is called image warping. In this paper, they proposed a way to learn the parameters of this transformation. So I have this T is some transformation. You can estimate the parameters of this transformation, which we call theta. So theta here is like estimated through a learning-based approach. So we have this network, neural network, where it is trained with normal backpropagation. But you will see that all of these operations, whether the applying the transformation, doing the warping, all of these are actually differentiable operations, and they can be included in a neural network. So you can take this theta and then go through, no need to go into the details, but like this grid generator and sampler, what it does is that it performs image warping. Let's say here you see like it went from this upright 3 and it's rotated to this one. So this grid generator and sampler is a differentiable way of doing the image warping. So this is here, the spatial transformers. They're mainly working 2D transformations. But in order to understand it, you need to actually understand projective geometry. You need to be able to understand what are the different 2D transformations. You need to understand how to apply image warping so that you can understand how they did this grid generation and sampling. So all of these is like I'm trying to hopefully motivate you into seeing why these are important concepts to go through. There is also there's also this approach, and I think this is ACVSS, if I'm not mistaken. There are a couple. So actually, it's not just one paper. There is a lot of works that are trying to estimate depth in a self-supervised fashion. Most of them are dependent on a good understanding of 3D and 2D transformations. If not, I would say all, and the camera models. So you will see that, and these are like, again, like very recent works in the depth estimation are still referencing these types of works. So if you go like, I mean, I can show you, let's actually, let me show you the paper. Like a lot of parts from that paper relies on just basic understanding even of like how to construct rotation matrices. Like for example, here, this is the rotation matrices that we were discussing about, like how to rotate around the x-axis or the y-axis or the z-axis, except that now these things are learnable. So we're learning the parameters for the transformation. And it's also including a couple of things regarding how to do, like how to do the projection from 3D to 2D, and how to transform 3D point cloud. So you will see it's, I'm not going to go through the details of the work. I'm just giving you a motivation on why understanding these concepts can help you for people who want to work in geometry and in computer vision with deep learning. So yeah, this is, for example, like the model itself is trying to estimate the camera motion and the object motion. So everything is being learned, but you don't have a signal, like you don't have a ground truth of what is the depth. you're just relying on the fact that you can, by getting this an initial point cloud that is predicted, you can transform the point cloud using your estimated camera motion. And from this transformed point cloud, you can project it back to the image and estimate an optical flow. And you can use that to ensure consistency. So if you're doing it between pairs of frames, so whatever has this transformed point cloud, when it gets projected, you want to make sure that there is some consistency. And the intensity is actually matching after applying this flow. I know you haven't yet got introduced to what is flow or what is optical flow. We're gonna go through it in the next, but I'm just giving you a hint that in order to understand these type of works, you need to have good understanding of what are the 2D and 3D transformations, how to apply them, the camera models, like how to do projection, all of these. So yeah, let me know if you have any questions. Okay. So if no questions, I'll go to the last. So this is the last tutorial. And so I'll go through the motion estimation today. If, let me see, yeah. Hopefully we're able to finish most of it. And if there is anything remaining, we'll continue it next time. And then I will talk to Helga about the remaining sessions. I think we'll discuss how to continue it because I won't be, so I can only do another Sunday as I'm traveling. Here. So if this tutorial is trying to go through how to estimate the apparent motion, and I'll describe what does it mean to be apparent. The apparent motion pixel-wise between if you have two consecutive frames. So this apparent motion is what we call as optical flow. I'm actually wondering, anyone here has worked with optical flow before or understands the basic concept of it? It's not as common, so it's okay, but I'm just wondering if anyone has worked with it before. No? Okay, so I'm assuming if no one responded, this is a new concept for all of you. So this is a necessary concept for if you are interested to work with videos, or if you want to go for 3D vision generally also. So what is optical flow? It describes the apparent motion. So if I have here frame 1 and frame 2, it will tell you the motion between these two frames. You can estimate it at certain points, at certain, like let's say we have corners. So at certain key points, I'm estimating the flow, or you can do it dense. So meaning every single pixel I want to know how it moved. But we're only getting apparent motion in 2D. So we're only estimating this change in X, change in Y coordinates, the pixel coordinates. So it's not the full, so there are some other works that go through estimating like something called scene flow. We're not going through that. We're doing the most basic. The most basic is trying to understand the apparent motion between these two frames in pixel coordinates, like 2D pixel coordinates. And it's very useful when you're working with videos. So you see here, I'm not sure if it shows, but you can see that there are some here vectors showing that the camera is actually moving. So you have this camera here and it's moving across the corridor. So you can see that the optical flow will then be estimated, that it's always moving in the like in the inverse direction of what the camera is moving, right? But again, it's only 2D. So we only estimate the change in X, change in Y, and that's it. You will find some people try to describe or represent, sorry, optical flow instead of delta x, delta y, like instead of having some vector, let's say 1, 2, which is describing that it moved in the x direction with 1 pixel, moved in the y direction with 2 pixels, we instead use colors. Like you have an RGB image like this. This RGB image is at the end using the polar coordinates. Like if you have here a certain point, x, y, if you have this vector, which is describing how you moved, you can always get the r and the angle, so the magnitude and the direction. And this magnitude and direction can help you to pick which color. So according to the direction, you can pick whether it's like blue or more on the red part. So this will tell you the direction of the flow, and the magnitude as well can help you with the color intensity itself. So this is another way to represent optical flow. Okay, I want to show you how it is. So if I so you see here, this here is what I'm talking about for optical flow. You can see that these colors here are the designating, like it's giving you a signal on the direction of motion. But then we're talking only 2D motion. Meaning I'll ask you a question. If I have a moving camera and there are no objects moving, am I still going to, for the optical flow, am I going to have 0 flow vectors, like nothing is moving? Or I am actually still going to have some motion? What do you think? Although there are no moving objects in the scene, just a camera that is moving, what do you expect? Yeah, let me know if
I think the object. So I was thinking maybe the objects will be moving the opposite direction.
Exactly, but yes, exactly. So if I'm moving forward, everything will appear as if it's moving in the inverse direction, and it will all appear. I agree with you, Grace. All appear as a single color. More or less, it's not going to be exactly one color, but we're not going to talk on why, because it's the depth of the objects also can affect how it appears to be moving. But we're not going to talk about that. That's more advanced, but there is something called parallax. So you know how if I'm moving, objects back at the far will appear moving differently than the objects that are quite close to me. But all of them will, at least like the direction of the motion, I agree with you, Grace, will, as long as there is nothing else moving, all of them should be, yes, in the appearing almost similar. So yeah, but now we actually have a moving object. So in this case, thank you both for participating. So in here we have both a camera moving and an object moving as well. So all of this is what I'm talking about, like how to compute this flow vectors, and you can compute them dense, like per pixel. This is what we're going to study. Like we're going to go through this session. Why do we care about optical flow? So you'll see some, a lot actually, some. I would say most of the methods before, like the recent ones, but most of at least the previous methods were using optical flow as input to perform, for example, segmentation of motion. Like if you have a moving object and you're trying to segment it. This is part of the research that I was personally doing. There are some, I just don't want to go through, yeah, that's just to save time. Some people also, when they were doing action recognition, they will also use optical flow as input to help you identify what are the type of actions that are happening in the video. Except that, yeah, I mean, some of the video understanding methods now are trying to move towards doing it implicitly. So with video transformers, you're not necessarily providing it with optical flow. But I can say, at least in video object segmentation, especially the automatic one, up to a very recent, like up to 2023, some of the works that I personally published, before it, everything was just using optical flow. So this is how important it is to understand, especially if you're working, if you're going for video understanding. So yeah, anyone has first any issue with just understanding the basic concept, like what is optical flow? Like why does it indicate like some this apparent motion in 2D between two consecutive frames? Okay, and we have gone even through also the motivation. What we're going to go through now is just a small math review, and then we'll go through the details of the method that we're gonna look into. So in order to understand the most basic optical flow estimation technique, which is called Lucas-Canada, I personally think it's important that you understand Taylor series expansion. And anyway, think of Taylor series as a mathematical tool. You will find it used widely across multiple things. So it's good to have this intuition, like what does it mean to do Taylor series expansion? First, have any of you used it before? Or this is the first time to look into it? Anyone used it? No? Okay, so I'm assuming again it's a new topic, so we're gonna go through understanding what is the Taylor series expansion. So Taylor series is mainly used to approximate a function with a polynomial. So I have here, see this red function. This red function, which I call fx, is actually a sinusoidal function, and it's just for as an example. And I'm trying to approximate it with this blue function, p of x. Now, p of x is a polynomial. You cannot use a sine cosine. It's a polynomial function. And I'm trying to create a universal way of approximating any function with this, with a set, with a series, with some polynomials. So in order to do that, one way, so we're gonna go through the intuition, like building the intuition for Taylor series. So you see here, you need at least to make sure that one point is correct. So the red function, if you go to f of 0, this is equal to 1, we can at least ensure that p is also at 0 equal to 1, meaning both have the same, are equal at this location at x equals 0. That's an initial part. So I can approximate p of x to be simply f of 0. Now, if you do this f of 0, it means it's all the time. So it's just instead of actually doing it's just one line. But this is a bad approximation, right? We don't want to go for such an approximation. It can be, so if you do p of x equal f of 0, p of 0, p of 0 is going to be equal to f of 0, which is going to be equal to 1. But here's the thing. I can claim that I can do this function here, and it is passing by this point here. Or I can do this function here, can do this function here. All of these are passing by this point, where both, like where I have p of 0 equal f of 0 equal 1. But they're definitely all bad approximations. This is not what I want. I would say this is a good approximation, and it does have p of 0 equal f of 0 equal 1, but it's still not, like it's a bit better, but there is nothing here in the original approximation that tells me that this is better. So one thing we can do is start using the derivatives. So I can tell my function, so the p of x, which is the approximating function, I can make it equal to f of 0 plus the f bar of 0, which is the first derivative, multiplied by x. So in this case, what happens is that it's not only that p of 0 is, so they're not only going to be equal at p of 0. So if you see p of 0 is just going to be f of 0 plus f bar of 0 multiplied by 0. So you can say that at least they're equal at point 0, but also their first derivative is equal. So not only I'm making sure that this point is the same, but I'm also making sure that the slope is the same. Okay. So if I say here p bar, so p bar, the first derivative of this function, this part will be a constant, and this f bar of 0 multiplied by x, so it just becomes f bar of 0. So now it is equal, p of 0 is equal to f of 0, and p bar of 0 is equal to f bar of 0. So I ensured at least one point is intersecting, and the slope at this point is also the same for both functions, p and f. But that's not sufficient, because you can have this function where you can see that both are, so they're both intersecting. So p of 0 equal f of 0 at this point, and p bar of 0 equal f bar of 0 as well. Both have the same slope. But this is not a good approximation with respect to this one. This one is better. So we can, instead of using the slope, we can use not only the slope, we can also go a bit higher and use the curvature, which is the second derivative. So you can start adding here the second derivative. So again, this is just building intuition. I'm not trying to derive. I'm just building you an intuition. What does Taylor series? What is Taylor series doing? So you can see here. Now I have additionally this f double bar 0 multiplied by half x squared. So if you take the first derivative, so the first derivative is just going to be f bar of 0, and the second derivative here, so I have half multiplied by 2x f double bar of 0. So I'm just doing first derivative, second derivative, sorry, first derivative. So this becomes f double bar of 0x. And then if I try to derive here, oops, sorry. If I try to derive this one again, so I'm trying to compute p double bar, it's just going, this is going to be discarded, it's going to be constant, and this is going to remain. So this is f double bar of 0. So now I have p of 0 equal f of 0, and p bar of 0 equal f bar of 0. So at point 0, they're equal, their slope is equal, and their second derivative is also equal. So the curvature is equal. So you are all the time trying to improve your approximation by using higher derivatives. So here, you can actually take that, sorry. Yeah. So you can take that a bit further and do the nth derivative, up to the nth derivative. So you are going to keep expanding. So you see here, this is another f of x, another sinusoidal, and another polynomial that I'm trying to use. So the blue one is the polynomial that I'm trying to use to approximate. So if I do the first order, it approximates a bit, but it's not the best that I can get. With the third order, it becomes better. With the fifth order, it becomes even better. So as you go, so this is fifth order expansion of the Taylor series means that you're including your fifth derivative, your fifth order derivative, okay? So as you increase the amount of derivatives included, this is what you get a better approximation, okay? I'm just hoping that this is like clear. Of course, again, I don't want to go through these details, but the Maclaurin is assuming with respect to the origin, the Taylor allows with respect to h, whatever h is. So this is like, it becomes more general. It's not necessarily the origin. And you can even approximate a function of two variables. So I'm always using a function of one variable. You can use two variables. And this is what we're going to use for the optical flow, by the way. So I have a function of x and y. So you can say it is equal to f of h1, h2. So this is with the point I'm evaluating, like expanding with respect to it. And then adding the first derivative partially with respect to x, first derivative partially with respect to y. So this is, again, I'm trying to build up your intuition. Remember here, I just went from the Maclaurin to the Taylor and added the difference. So this is, you can say that this is the delta x. You'll have here delta x all square until delta x all power n. And here I have delta x and I have delta y because I have two variables. So just again, as a summary, before we go to the optical flow, just want to make sure, is the intuition itself of Taylor series make sense, or do you feel like you're still confused? So if I ask some of you, like in layman terms, okay, I see, Grace, you're saying that you learned it in the undergrad. Okay, thank you for highlighting it. So again, that's great. So if you already have gone through it before, that's great. I just wanted to refresh your memory about the intuition, because usually if you took it, you probably didn't accumulate that intuition until you start looking into how it's being used in optical flow. Things can be confusing. So just keep in mind, we're trying to approximate a function using a polynomial. And you can use, and I'm showing you here a first order expansion, meaning that it's using first order derivative. A second order expansion will use the up to the second order derivative. As you increase the derivative, like the order, it becomes a better approximation. It becomes more difficult to compute though. So no questions, or just making sure everything is good? Okay. Okay, so I'll go through, yeah. Let's do in a bit of the optical flow, just the basic assumption, and then I'll next time we can continue more on it. Thanks, Grace. And no worries about it. So the base of optical flow is actually, we're gonna do a Taylor expansion. That's what we're going to do in optical flow. But first, we need to understand this brightness constancy assumption. So brightness constancy assumption, it assumes, and this is not always true, but we are going to assume that when you go, so if I have here frame 1 and I have here frame 2, and I'm trying to compute the optical flow, which is the apparent motion between these two consecutive frames, we're assuming the pixel intensity. So if I have this here pixel, I'm trying to estimate its motion in the next frame, pixel intensity will not change. It will stay the same. This is violated by a lot of other things. Like you can have, if you have, for example, a flashlight, and you just put a flashlight on the during the video, you just change the brightness, right? But we're up to, like, there are some failures for optical flow, but up to an extent, we're trying to like simplify things. So we'll put this assumption. That's why it's called an assumption, that the brightness is constant. So if I have here x, y, and t, so I have a function of 3 variables. I have a video at the end, so I have 3 variables. The x, the y, these are the spatial positions, and the t in time. They're going to be equal to this. So like this point here, I'm gonna say this is here the f, x, y, and t. Is going to be equal, like the brightness will stay. So f here is the intensity function. The intensity will stay constant, taking into account that this pixel moved with the dx and dy, and in the new frame plus dt. So this is the main rule that we're going to build upon everything. So this is called brightness constancy. There is another constraint that we will rely on in the Lucas Canada. It's not, so Lucas Canada uses some local constraints, and this is what we're going to go through. There are a lot of other techniques for doing optical flow. We cannot cover it in one lecture or one session. But we'll just do the most basic one for the understanding. So anyone has any issue with the brightness constancy? If I, like this point, this intensity, sorry, is going to stay the same for the same point after it changed, moved with the dx and dy in the new frame after dt. Okay. Yeah, just confirming. Okay, so if any questions, let me know. So we're gonna do a Taylor expansion. So you see this? I can do a Taylor expansion and say that it is equal to fxyt. We're gonna do a first order expansion, meaning I'm gonna only use the first order, derivative. And I have 3 variables. So I need to make first derivative with respect to, partially with respect to x, partially with respect to y, partially with respect to t. And each one gets multiplied by the delta in x, delta in y, delta in t. So it gets multiplied with the change in its component. So anyone has any issue? So I'm trying to approximate, like we're doing just the normal Taylor expansion that I showed you earlier. Anyone has any issue so far? Everything is good? Okay. So based on this brightness assumption, we're just going to simplify things. So like we're gonna take these out. And based on this brightness assumption, we are gonna do, so this is, we're gonna just call it fx. So this is the first derivative with respect to x. And this is, we're gonna call it fy, first derivative with respect to y. And this is ft. This is going to be equal to 0. Okay, because we just deleted these two. Yeah, just rearrange things and remove the ones that can go together. And then the optical flow vector is actually the dx and the dy. So the change in x and the change in y. This is what we're trying to estimate. So if I go from here, let's say this point, it moved 2 pixels in the x, 1 pixel in the y. This is my UV, and it became here in this new location. So this is what I'm trying to compute. And dt, you can just assume 1. Like I'm just changing from one frame to another. Like, yeah, I mean, it's we're just trying to estimate it, not sorry, put a way to estimate the u and the v. And that's what we care about. So we're gonna need the gradients with respect to in the x direction, y direction, and the temporal one as well, like in the t. And all of this is what constructs this equation. But now I have how many unknowns? Like how many things I'm trying to compute? Remember, just as a refresher. How many equations now I have and how many unknowns I'm trying to compute? What do you think? So how many, we all agree. I mean, I have one equation, right? I have one equation here, which is fxu plus fyv plus ft equals 0, which we derived through this assumption that the brightness is constant. That the object, as it moves, the pixel will change, yes, but the intensity will not change. As an assumption. But how many unknowns I'm trying to compute? Anyone remembers? What am I trying to compute? Just want to make sure that we're all on the same stage. What do you think? I mean, you can guess. Yeah, I mean, have you, if you haven't, I know if you haven't encountered optical flow before, but from what I derived, remember what I'm trying to do. I'm trying to compute optical flow. Exactly. Exactly. Sorry.
Sorry, that was me. I thought it would be U and V.
Exactly, Daniel. Thank you. So it's U and V, or like the change. So I think Loyan, what he meant means the dx and dy. So it's the change in x and the change in y. Now the change in t, Loyan, we don't need to estimate. So we assume that it's just changing. So from one frame to another, from one frame to, so assume one for now. We're just trying to estimate the change in x, change in y between these two consecutive frames, regardless of the exact dt. Okay, so assuming this is one. So we have two unknowns, one equation. This is under like we don't have all the constraints necessary to solve it. It becomes under constraint. So this is going to be a problem. We'll need more constraints to be able to solve this equation. But this is the optical flow equation. Like if we, this is the main one. And then there are various ways of solving it. One is the Lucas-Canada, one of them. It's not the only one, but one of them is the Lucas-Canada that we're going to cover today, which is a very classic approach. But it's important to understand because a lot of the new approaches are actually inspiring from these classical ones. Okay, so let me clarify what does it mean to be under constraint. So you have here, this is a line equation, right? So I can have, I just rearrange things. So I basically divide by Fy and then rearrange these to go the other way. So this equation here, if I plot it, you will find that the solution lies on this line here. So if I have this point, it means the solution is can be actually how to say, I forgot the term for it, but it can be like divided into the D and the P. So the D, this is what we call as the normal flow, and the P, this is what we call as the parallel flow. So this is one solution. Because I only have one equation, I can have multiple solutions because it's under constraint. Like I only have one equation and I have two unknowns. Another solution can be here. Another solution can be here. All of these are solutions to this equation here that will all make it equal to 0 and all following the brightness constancy assumption. But you can see in all of these, what is mainly changing? The parallel flow. So all of them have common normal flow, but the parallel flow is changing from each of these solutions. So if I go here, this P here is different than the P here. So this is just factorizing the into the normal and the parallel flow. So this is what we call, so you will find something called aperture problem. It's some ambiguity that happens because of the fact that we're only able to determine the normal flow. We're not able to determine accurately the parallel flow. So the normal flow, so you see here, if you look into this part, so just here, the one that I'm highlighting, you see this is telling you that the object is moving from left to right. It's quite clear that it is moving from left to right. But the problem, this can, like the full object motion is not like that. The full object motion is actually moving diagonal from top left to bottom right. So this motion here, this is the correct one. But this is what you perceive. And there are ambiguities that arise. So what we will, in order to solve for these ambiguities, we're first going to assume local constraints. We're gonna have more equations to make sure that we can solve for the two unknowns. And we're gonna make sure as well that we compute them at locations where we define corners. So we resolve these ambiguities, okay? So we're gonna need, first, we're gonna define the extra constraint. I just wanna make sure, yeah, before we move, everyone understands where is the problem. So this is the motion direction. The motion direction can be into the normal flow and the parallel flow. But we are only able to capture the normal flow, this one. The parallel flow, because we're not able to see the full object motion, there is some ambiguity arising. So this parallel flow, we're not able to determine. And it is related to the fact that you're only seeing, you're only able to identify the normal flow. So we're gonna solve it on multiple steps. First, we need to before starting anything, we have one equation and we have two unknowns. So of course we need to increase the equations. So let's do that first. So the extra constraint here is the local one. So a local constraint is that we're going to assume that locally, like let's assume like a 3x3 area of pixels, there's some smoothness in the motion. So the motion of this pixel is gonna be similar to this, all of these. So this 9 pixels are all going to have the same motion. So it's called like smoothness. Now, this local smoothness constraint gives you an overdetermined system. Anyone knows why it's called overdetermined? What does it mean to be overdetermined? If you have a system of equation that you're trying to solve, when I say that this system is overdetermined, what does it mean? Look to how many unknowns and how many equations I have. I'm not going to describe now like this part. So like don't look into it, but just look to the simple equation here. So this is the simple equation that I started from. How many unknowns do I have? So unknowns and equations. What do you think? So I'm trying to estimate optical flow. So we talked about how we're trying to estimate the U and the V. So how many unknowns? Anyone wants to volunteer? 2, exactly. Thank you, Daniel. So we have 2 unknowns. How many equations now? So initially it was just 1 equation. We're trying to estimate it per pixel. But we started to do this local smoothness constraint where I have a 3, let's assume 3x3 neighborhood. This is a hyperparameter. So I have a 3x3 neighborhood, and I'm assuming that they're locally moving the same. So how many equations I can get from this 3x3 neighborhood? How many equations? Any suggestions? Meme Diara, 3. We're doing 3x3. So for each pixel in the 3x3 neighborhood, we are gonna have its own equation. So then we have 9, exactly. Thank you, Daniel. And thank you, Meme Diara, as well. So we have 2 unknowns, we have 9 equations. That's why it's overdetermined. So it's if I have less, it's a problem. I need at least 2 equations, but with this local smoothness constraints, you can have actually more, which is better because you can have a better, you can reduce errors. So I'm gonna use this 9 equations to construct this overdetermined system. So remember, if you remember here from the brightness constancy, this fxu plus fyv equal negative ft, or plus ft equals 0, it's the same. So this is the equation that I'm going to repeat for every single pixel in this 3x3 neighborhood. So I'm gonna do fx11 fy11 multiplied by uv is equal negative ft11. Similarly, I'm just here putting it as a matrix vector multiplication form. So this is the second pixel, fx12. So I have here, this is x11, x12, x13, and so on. So this is the second equation. And I'll have a third, and so on. And this is the last one, fx33, fy33 multiplied by uv. And then this is equal negative ft33. So I have here a 9 by 2 This is for coefficients for the system of, like, this is my system of equation, a linear system of equations. And I have 9×2 matrix for the coefficients. This is 2×1 vector UV, the optical flow vector that I'm trying to compute. So this is the unknown. Okay. And I have here the solution, this 9×1 vector. This is an overdetermined system. How do you generally? So this is something, I mean, it's not just in computer vision, like generally, if you have any overdetermined linear system of equations, how can you solve it? There are multiple ways, but the most basic one, it's a linear system of equation and it is overdetermined. What should I do? I have just Ax equal B, where A here is this 9×2, X here is the vector of the optical flow unknowns, the UV. So what do I do? Anyone knows what can I use to solve this overdetermined system? No? Okay. So I'll tell you that this, we can just use linear least squares. And there are various ways even of like how to exactly compute it. But at the end, just a least square solution. We can do a least square solution. Exactly. You can, but this is not the best way to do it, by the way. So you can do a pseudo inverse. It's just because of the so if you do inverse of the matrix, it can have its own issues. We're not gonna go through. This is a bit linear algebra, but there are various ways of doing the least square solution. But we usually don't do A inverse. But anyways, you can do a pseudo, like you can do some pseudo inverse and get at the end the final X. So this is good. Just the only problem with the least square solution, if you have an outlier, it messes up the final output because you're taking into account everything. So that's why people sometimes use like whenever you have an overdetermined system and you're trying to solve and you want to get rid of outliers, you can go for other other techniques like Ransack or other things. But the most basic one that is used in Lucas, Canada, we just use any form of a least square solution and we just use it directly. Okay. So yeah, I mean, I think we can stop here, and yeah, next time. So this is the least square solution. Next time we're gonna go. We can go through it in a bit more details, and then see how to. So I'll show you at the end. This is the final equation we will be using, which is actually the so this is derived from doing the least square solution, and this is where we will try to show you how to compute these. So this is the image gradients, we talked about it, and these temporal gradients, we're gonna go through how to compute them. So yeah, I'll leave that for next time better, and then we'll see also how it's better to also compute them around the corners to avoid ambiguity in defining the motion. So all of these are going to be discussed next time, in addition to a bit going through a bit of using optical, like how optical flow now is being estimated. So there are a lot of works. Yeah, there is always a new work on how to estimate optical flow with deep learning. So these are faster, more efficient, more accurate, sorry, solutions. So yeah, let me know if you have any questions so far. Okay, so assuming, yeah.
I think the only question that I have is the third component, the FT, the temporal thing. I don't really get, because I get the X and Y coordinates of the pixels, but the temporal, I was thinking it's the frames, but I saw at least as you're doing T11, T12 for the over, I don't know what you call this again.
So your question is how to compute FT, right? Like what does it mean even to have temporal gradients? So remember, I'm from the start, my input is 2 images, right?
Okay.
So you can, there is a way, and I'm going to talk about it, but let's leave it better for next time, because so next time I'm going to focus on all the details of how to actually compute optical flow. So the temporal gradients is just, remember when we did the image gradients, like the spatial in X and Y, we had this filter, we talked about the Sobel filter, and we filtered the image, we did the convolution on the image, and then we ended up having the gradients in the X, gradients in the Y. We're gonna do something very similar, except that now we're including both images, because it's a temporal, it's between the first and the second. So FT is the change in the intensity, but across the time dimension.
Oh, all right. All right.
So it will just be another filtering operation.
All right. Thank you.
Oh, no worries, no worries. Thanks. Yeah, let me know if you have any questions. I'll try to prepare. I couldn't prepare a practical for the 3D transformation, so I was quite busy, but I'll try my best to prepare a practical for the optical flow for next time, that we can experiment a bit, in addition to continuing of the explanation of optical flow. So next time will be the last one. And I'm hoping these are, again, establishing just the basics, especially in geometry. I know it could be a bit hard to understand the math behind it. So if you need any questions, you can get back to me as well, or Helga. He's amazing in it as well. And yeah, thanks for coming, and yeah, see you on Thursday, hopefully. Thank you.